Okay, good afternoon. Today we're going to talk about the Lagrange error bound. So you all should have a handout to take notes in. So I'll save you some writing today here. So yesterday we developed some Taylor polynomials, and we developed them so that we could approximate a function using a polynomial. Now we know that that is not going to be exact. There is going to be some room for error, and so the Lagrange error bound is the error calculated in using the polynomial to approximate the non-polynomial function. Okay, it's going to be a little bit like the alternating series error. They're based off of the same concept as far as the next unused term. Okay. So you see written here, we have our function is going to be whatever our polynomial is plus the remainder, right? Okay. Or our remainder is the difference between our function and our polynomial. Okay. Well, this is what it's going to look like. So here is the difference between our Taylor polynomial and our function. And our maximum error is going to be given by this right here. First of all, it's an absolute value. It could be a little bit over or it could be a little bit under. We're not sure. And so we do the absolute value, and then later we'll add and subtract it to whatever that exact value is to illustrate the error. Okay. Now, we know that when we make our terms, and I'm going to come down here, we have our function evaluated at whatever we're centered at. And then the derivative evaluated at wherever we're centered times x minus c. And then the second derivative over 2 factorial, and the third derivative over 3 factorial, etc., etc., etc. So if we are talking about the nth Taylor polynomial, then the next term would follow that same line, where we have the derivative, the n plus 1 derivative, right? So if we're talking about the 5th degree polynomial, this would be the 6th derivative. If it's the 7th degree polynomial, we're talking about the 8th derivative. Okay, so the next derivative over the next factorial multiplied to the next, whatever that power is. Okay, now all of this looks fine and dandy, but Mrs. Holman, this is a z. What is that? Okay, well, we want to maximize our remainder. Okay, some of our functions, and especially if we're not using a calculator, which is a lot of times what we use the Lagrange error bound for, right? Obviously, we can figure out what the sign of 1 is with our calculator, but can we approximate the sign of 1 without our calculator? That's why we would use a Taylor polynomial. So without our calculator, we're going to think about what is the maximum that next derivative would be in order to really understand how big of an error we could have. Okay, so this is just giving us a little bit of cushion. Okay, so we need to think about this z in the interval x to c or c to x, depending on what we're looking at here. What would be the maximum derivative on that interval? Okay. What I want you to think about this, just like we did with the alternating series error, is that this is the next unused term. The only difference we're going to have is we are wanting to maximize our next derivative. Okay, and so I want to show you the different ways we need to think about that. Okay, so there are a lot of different ways these problems can be asked. And so I'm going to illustrate, it looks like, 4 examples for us, so we can see the different types of questions you may encounter. Okay, I will warn you that this is a huge thing on the AP test, okay? We're really going to hammer it hard because you'll see it multiple times on your AP test. So, we have a function with 5 derivatives on the interval 2 to 3. Okay, there's our interval that we would need to be worried about the max derivative at. Okay? Assume, here we go, assume that the 5th derivative is always less than 0.2 in that interval, and that the 4th degree Taylor polynomial centered at C equals 2 is used to estimate f of 3. Okay, how accurate is this approximation? So we're talking about a 4th degree polynomial. So our remainder, or our error, for our 4th degree polynomial is going to be as such. We want to worry about the 5th derivative, its maximum, over, since we're talking about our 4th polynomial, over the 5 factorial times x minus c to the 5th. Okay, what are all these numbers here? C is what we're centered at, and we know that we're centered at 2. Okay, now, centered at 2, okay, we're using it to approximate 3. All right, so we know it's going to be close because you saw all those graphs yesterday, how the further, the more terms we added, the closer it was even around where we centered it at. Okay, so at 2, exact. Away from 2, a little bit off. So that's what we are approximating. Here, squiggly line, that's where we're centered. Okay, now our max derivative, it tells us that our max derivative is 0.2. So we're going to go up here and we're going to change this to 0.2. Okay, so let's talk about what this is. We have 2/10 divided by 5 factorial times 1 to the 5th. Five factorial is 120. So we have 0.2 divided by 120 times 1. We know our remainder is going to be less than or equal to 0.002. Now, suppose that the polynomial evaluated at 3 is 1.763. Okay? Use your answer in A to find an interval in which f of 3 must reside. Well, this is our maximum error, and they're telling us that this is the approximation. Okay? So our exact value of f of 3 is going to be 1.763 plus our maximum error and 1.763 minus our maximum error. Okay? So f of 3 is going to reside in the interval 1.761 to 1.765. Okay? To me, that's a fairly good approximation. Okay, we're not going to be off by too terribly much. Okay, now, I'm going to erase this here. I'm going to pull this interval. Cool. Okay, so could f of 3 equal 1.778? No, because it's not in the interval that we just found. Okay, could f of 3 equal 1.764? Yes. Same reason, or opposite reason, I guess. It is in the interval that we just found. Okay. All right, now that one was nice because they gave us all the information verbatim, okay? Plug these numbers into this Lagrange error bound formula. Now, let's actually look at, and they don't. Okay, find the fifth degree Maclaurin polynomial for sine of x. Use your polynomial to approximate sine of 1, and use Taylor's theorem to find the maximum error in your approximation. Give 3 decimal places. So, here we go. F of x equals sine of x. We know evaluated at 0, because we're talking about a Maclaurin, is 0. We know f prime of x is cosine of x. Evaluated at 0 is 1. Okay, our fifth degree polynomial. And so I'm going to call it P sub 5. P for polynomial, 5 for that fifth degree of x is going to be 0 plus 1x plus 0 minus 1 over 3 factorial x cubed plus 0 plus 1 over 5 factorial x to the fifth. Okay? Now, if we want to approximate sine of 1, okay, this is centered at 0. We just centered our polynomial at 0. So if we want to approximate 1, we can plug 1 in to our Taylor polynomial to get an approximation. Okay, so 101 over 120. Okay, now I want the Lagrange error bound. So if I'm using our fifth degree Taylor polynomial to approximate the sine of 1, how different is that going to be from the actual value of sine of 1? Okay, so our remainder for the fifth degree polynomial at 1, okay, is going to be, we need to think about how big our sixth derivative could be over 6 factorial times x minus c to the 6th. Okay, so we're centered at 0, that's why this is 0. And since we're approximating at 1, that's why that number right there is 1. Okay, well, let's think about the sixth derivative. Our sixth derivative would be negative sine of x. And here's the deal. We don't have our calculator, and this is going to be just pretty straightforward when we have a sine or cosine curve. We know that our sine and cosine curves bounce between two values. We have an amplitude for each of those curves. In this case, since the coefficient of sine of x is -1, or if it were +1, our amplitude would be 1, which means the highest it could go is +1, the lowest it can go is -1. So no matter what our sixth derivative, the highest it could ever go, positive or negative, would be 1. Okay? So we know that we are going to be off by at most 1 over 720. Okay? Which means the sign of 1 is going to be in between what we approximated it to be plus the error, what we approximated it to be minus the error. I'll save you some time here. This would be 607 720ths and 605 720ths. If we were to approximate that with a decimal, we'd be here. Okay? With a polynomial, we can get pretty darn close. Now, could the sine of 1 equal 0.9? The sine of 1 cannot equal 0.9 because it is not in this interval right here that we just created. The sine of 1 has to be in between those two values. 0.9 is not in those two values, so the answer is no. Okay. Let's try another one. Write the fourth degree Maclaurin polynomial for f of x equals e to the x. Then use your polynomial to approximate e and find a Lagrange error bound for the maximum error. Okay. So what I want you to do is come up with our polynomial for e to the x. Okay, so hopefully you saw the pattern, right? All of our derivatives are e to the x, e to the first, e to the 0 is 1. There we go. There's our polynomial. Best polynomial we create ever, right? So we want to approximate e. Well, that would be when we plug in 1 for x. So e to the first is going to be approximately our polynomial evaluated at 1. Which would be 65/24. Okay. So now let's talk about our error. Our remainder, so our error for this fourth degree polynomial is going to be the maximum that our fifth derivative would be over 5 factorial times, this is centered at 0 and we're plugging in 1. Okay, now let's think about our derivatives for e to the x. Our fifth derivative is going to be what? E to the x. All right, now, you don't have a calculator for this example. Okay. If we think about the graph of e to the x, and we're on the interval 1 to 0, because we're centered at 0, we're approximating at 1. Technically, okay, since this increases indefinitely, then our maximum would occur here at x equals 1. What would our maximum value be? It would be e to the first. Now, without a calculator, we're not going to plug in the number e. But what would give us a little bit bigger cushion that is close to e? We're going to plug in 3. So we know that our error is going to be less than, and really it is going to be less than. We probably shouldn't even put that equals there because really it's e over 120. But we're putting 3 over 120, so it's easy for us to work with here. So what would be the interval that e would be in between? Okay. If we take 65 over 24 and add, our error, and then if we take it and we subtract our error. And I know those aren't reduced. Feel free to reduce them if you wish. But when we're working without a calculator, I'm not going to get too picky about that. Okay. Okay, and our last example. Okay, so here we are given the derivatives at 2, good thing, because they're asking for a third degree polynomial about x equals 2. So our function, we are going to approximate it with our third degree polynomial would be, all right, our function value is 6 plus our first derivative is 4. Remember, we're centered at 2. Plus our second derivative is negative 7 over 2 factorial. Plus our third derivative is 8. Now, if you would like, feel free to reduce this down to where we have 7/2, so I guess that's not really reducing, but just rewriting it. But we could reduce this to 4/3 if you wanted to. Okay? Now, use it to approximate f of 3. So, 2.3. F of 2.3, we're going to use our polynomial to plug it in. Would be 6.921. We're going to plug 2.3 into each one of those x's and get 6.921. Okay. Now, and this is nice. I like this example because it's really explaining to you what it means, or to find that max derivative on the interval, and it really lays out the interval for you. Okay, we approximated at, or we wrote our polynomial at 2. We approximated it at 2.3. That is the interval we're worried about. The max derivative on that interval is 9. Okay, so if that's the case, then the error, or the remainder is what we like to call it, on that interval is going to be the max of our fourth derivative over 4 factorial times, okay, we centered at 2, so we typically have x minus 2 to the fourth power in this case, but we approximated at 2.3, so that's what we're going to throw in there. Now, we know that that fourth derivative is less than or equal to 9. So we get that our error is less than or equal to 0.00303. What does that mean? That means that f of 2.3 is going to be in between. We can take this number right here and add our error and subtract our error. Okay, this is the interval that f of 2.3 would fall under, which would mean that part C, could it be 6.992? No, it can't, because it's not in that interval that we just found. So this is what I need you to do. The sub is going to hand out your worksheet. Please work on this worksheet. We'll go over this worksheet tomorrow. If you had any issues over last night's homework, please talk about that as well with your peers. We will see you tomorrow.